So force vector directed along a line. Take a look at this diagram here. We have this cable or a rope that has endpoints at A and B and some force that's acting on the rope. The rope is being subjected to this force in the direction of that axis here from A to B. So often the direction of a force vector is specified by 2 points like A and B through which its line of action passes. If the magnitude of the force vector F is known and the coordinates of A and B are known, then we can establish a vector expression of vector F by noting that vectors R, U, and F are all collinear and share the same direction. So they have the same line of action and the same sense of their direction. So position vector R, we just learned about position vectors. That would be the position vector, fixed vector in space that goes from A to B and has units of length. The unit vector would be the unit vector in that same direction, a dimensionless unit vector, okay, in the same direction as vector R. And vector F is also along that same direction, same line of action for all three of these vectors, where vector F, as we know, would have units of force. Keep in mind, however, as we just mentioned, that each vector R, U, and F has a different definition and distinctly different units. By determining the position vector R from A to B, then establishing the unit vector U, we can express the force F as follows. So vector F, force vector F equals the scalar magnitude of the vector, F without bold, times U in bold, the unit vector that defines its direction, the unit vector that goes from A to B in the direction of R and F. Okay, we know that the unit vector can be written in terms of the position vector from A to B. That would be the vector R over its scalar magnitude R. So putting all this together in one line, we would have the following vector expression for force vector F. We can find the Cartesian vector expression for force vector F if we know its magnitude F and we know the coordinates of A and B. So therefore, the general expression to find vector F, if we know those things, would be the scalar F times all of this in parentheses. On top, inside the parentheses, we have xb minus xa times I hat plus yb minus ya times j hat plus zb minus za times k hat. And then on bottom, all over the magnitude of that position vector, square root of the sum of the squares of the components, right? It's always how we get a magnitude of any vector. If we know its components, x, y, z components, we take the square root of the sum of the squares of the components. So that would be a general expression to get vector F based on all these other given parameters. So I generally recommend to do a step-by-step process where you first establish the position vector from A to B, okay, that's our vector, then calculate our magnitude using this equation here, square root of the sum of the squares of the components, and then divide vector R by scalar R to get the unit vector in that direction, okay, a dimensionless unit vector, you have that expression. Finally, multiply that times the magnitude of the force vector. Usually that's given in the problem. And then you'll have a full Cartesian vector expression of this force vector F.